In this video, we'll explore the reactions and versatility of ethers in organic chemistry. We'll start by reviewing some fundamental properties of ethers, including their synthesis and cleavage, and revisit their utility as protecting groups. Next, we'll examine the chemistry of epoxides, focusing on the different conditions for epoxide ring opening and their utility as electrophiles in reactions with Grignard reagents. Let's start with a quick review of ethers. Ethers are organic compounds with the general formula ROR, where an oxygen atom is bonded to two carbon groups. These compounds are derivatives of alcohols, can be synthesized from alcohols, and can also be cleaved to regenerate alcohols. In a previous video, we covered the synthesis and cleavage of ethers as part of a broader discussion on alcohol reactions. For a review of these reactions, feel free to check out the linked video in the description. Now that we've covered the main reactions of ethers for this course, let's move on to the chemistry of epoxides, beginning with a review of their structure and a discussion of their properties. Epoxides are unusually reactive cyclic ethers, capable of participating in several reactions that are not typically observed with other ethers. Consider the example of ethylene oxide. Its interior angles form a triangular structure with bond angles of approximately 60 degrees. Similar to cyclopropane, this bond angle deviates significantly from the ideal tetrahedral angle of 109.5 degrees for sp3 hybridized carbons, resulting in substantial ring strain and contributing to the high reactivity of epoxides. Because of this considerable ring strain, epoxides are highly reactive and readily undergo ring opening reactions, often popping open to relieve the strain. Furthermore, due to this strain, epoxides attached to rings must have both CO bonds of the epoxide in a cis configuration at the ring junction. A trans configuration would introduce excessive additional strain, making it too energetically unfavorable. Let's take a look at a few examples of epoxide ring opening reactions. Epoxides, like other ethers, can undergo ring opening under acidic conditions. However, due to their significant ring strain, epoxides can also be opened under much milder conditions, even in the absence of a strong nucleophile. For example, reacting the following epoxide with aqueous acid H3O+, causes the ring to open, forming a vicinal diol, also known as a glycol. The term vicinal refers to hydroxyl groups on adjacent carbons, while diol indicates the presence of two hydroxyl OH groups in the molecule. We observe a similar pattern with epoxides bonded to another ring, such as this other epoxide. This reaction would not occur with ethers like diethyl ether or tetrahydrofuran. While protonation of the ether oxygen creates a good leaving group, the conjugate acid or water is not a strong enough nucleophile to cleave the ether via an SN2 reaction. In such cases, a strong acid like hydrogen iodide is necessary, as its conjugate base iodide acts as a sufficiently strong nucleophile to cleave these ethers. Secondly, unlike most ethers, epoxides can be ring-opened with aqueous base. Treating the same epoxides as before with sodium hydroxide in water also gives very similar vicinal diols. Again, this reaction would not occur with ethers like diethyl ether or tetrahydrofuran. Without the presence of acid to protonate the oxygen of the ether, we cannot make it into a good enough leaving group for any substitution reaction to occur. As we've just discussed, epoxide ring opening can be conducted in either acidic or basic conditions. In the case of our first example, acid or base catalyzed ring opening gives us the same vicinal diol product. However, in the second reaction, we can observe a difference in the stereochemistry of the vicinal diol products. Let's explore the mechanisms of these two reactions to clarify the process of epoxide ring opening under acidic and basic conditions. Under acidic conditions, epoxide ring opening can proceed via either the SN1 or SN2-like pathway, and predicting which pathway occurs often depends on analyzing the products. Both pathways, however, share the same initial step. The oxygen atom of the epoxide is protonated by the acidic protons of the acid in an acid-base reaction, creating an excellent leaving group. Students often find it challenging to identify the leaving group and the alpha carbon in this reaction, so I've highlighted them in blue for clarity. It's important to note that even though the leaving group doesn't completely dissociate from the molecule, it's still considered a leaving group because the bond to the alpha carbon is broken, which is the defining characteristic of a leaving group. In the SN1 pathway, the leaving group departs, resulting in ring opening at the more substituted carbon, which is better able to stabilize the resulting carbocation intermediate. This intermediate is a chiral due to the planar geometry of the carbocation, allowing the nucleophile, in this case water, to attack from either side. In the SN2-like pathway, the nucleophile, in this case water, directly attacks the more substituted carbon of the epoxide. Under acidic conditions, protonation of the epoxide increases the electrophilicity of the more substituted carbon, making it the preferred site for nucleophilic attack. This attack occurs through a concerted mechanism, simultaneously breaking the bond to the leaving group and forming the new bond, resulting in inversion of configuration at the site of attack. As a result, this pathway produces only the inversion product, yielding a single enantiomer as the product. We call this pathway SN2-like rather than SN2 because it deviates from some standard SN2 rules. While both mechanisms involve a concerted process where the carbon nucleophile bond forms and the carbon leaving group bond breaks simultaneously, the acid-catalyzed epoxide ring opening differs in key ways. Notably, the nucleophile, despite being relatively weak, attacks the more substituted and sterically hindered carbon, a behavior that runs counter to the typical steric preferences of a standard SN2 reaction. This deviation is driven by the protonation of the epoxide, which increases the electrophilicity of the more substituted carbon, overriding steric considerations. Protonation of the epoxide reduces the electron density on the oxygen atom, causing it to pull more strongly on the bonding electrons it shares with both carbon atoms in the three-membered ring. This uneven electron distribution introduces partial carbocation character, with the more substituted carbon bearing a greater positive charge. The more substituted carbon can stabilize this partial charge better than the less substituted carbon due to inductive effects, similar to the factors that determine carbocation stability. As a result, the more substituted carbon becomes a stronger and more electrophilic target for the nucleophile. In cases where the nucleophile is poor, as with water, increasing the electrophilicity of the electrophile, in this case the protonated epoxide, significantly enhances the likelihood of a reaction. This principle mirrors why SN1 reactions, which proceed through fully developed carbocations, can occur even in the absence of strong nucleophiles, because the highly electrophilic intermediate compensates for the nucleophile's weakness. This three-membered ring opening pathway is an important concept that we will revisit in a future video. In contrast, under basic conditions, epoxide ring opening proceeds exclusively via the SN2-like mechanism, with the nucleophile attacking the less substituted carbon, where steric hindrance is minimized. This attack results in inversion of configuration at the site of attack, producing a single enantiomer as the product. The reaction of epoxides into vicinal diols under basic conditions occurs via a two-step process. In the first step, the nucleophile hydroxide attacks the less substituted carbon of the epoxide in a concerted SN2-like mechanism, breaking the ring and forming an alkoxide intermediate. While alkoxides are generally poor leaving groups, the significant ring strain of the epoxide drives the reaction forward. In the second step, the alkoxide intermediate is protonated by water, yielding the final vicinal diol product. Epoxides can be ring opened under both acidic and basic conditions using nucleophiles other than water. For example, alcohols or hydrohalic acids can effectively participate in epoxide ring opening reactions. Under acidic conditions, this typically involves an alcohol and a catalytic acid, while under basic conditions, it involves an alcohol and its conjugate base as the nucleophile. In the case of hydrohalic acids, the halide conjugate base participates in the ring opening of a protonated epoxide under acidic conditions. The halide ion acts as a nucleophile, attacking the more substituted carbon of the epoxide and forming a halohydrin as the product. When performing acid-catalyzed ring opening, it is important to ensure that the catalytic acid has a conjugate base that is poorly nucleophilic, or that the concentration of water or alcohol as the solvent is much greater than the concentration of the acid and its conjugate base. This ensures that water or alcohol serves as the primary nucleophile, yielding the desired product instead of a mixture of byproducts. It is also important to consider the compatibility of the nucleophile with acidic conditions. If the nucleophile is too basic, it will undergo an acid-base reaction with the acid rather than participating in the desired epoxide ring opening reaction. Finally, despite their high reactivity, epoxides require either a good nucleophile under basic conditions or protonation under acidic conditions to proceed with the ring opening reaction. If a weak nucleophile, such as water or alcohol, is used in the absence of a strong acid, no reaction will occur because the nucleophile alone is insufficient to activate the epoxide or overcome its stability. As we just discussed, epoxides can be opened using nucleophiles other than water. Notably, they can react with Grignard reagents in Grignard reactions, where the epoxide serves as the electrophile. Until now, the only carbon-based electrophiles we've seen Grignard reagents react with are carbonyl carbons. In carbonyl compounds, the significant dipole toward the oxygen atom gives the carbon a partial positive charge, making it electrophilic. Similarly, in epoxides, the carbons in the three-membered ring are electrophilic due to the dipole moment toward the oxygen atom. Additionally, their reactivity is significantly enhanced by the considerable ring strain, making epoxides highly reactive electrophiles in Grignard reactions. Reacting a Grignard reagent with an epoxide results in the addition of two carbons adjacent to each other, with a primary alcohol forming at one end. This occurs as the nucleophilic pair of bonding electrons in the Grignard reagent attacks the electrophilic carbon of the epoxide, causing the ring to open. The reaction is completed by an acid hydrolysis step, which generates the primary alcohol. It's important to note that the reaction of epoxides with Grignard reagents results exclusively in ring opening at the less substituted carbon. This selectivity arises from the SN2-like mechanism of base-catalyzed ring opening, where steric hindrance at the more substituted carbon discourages nucleophilic attack. Furthermore, introducing an acid to promote ring opening at the more substituted carbon is incompatible with the Grignard reagent. As a very strong base, the Grignard reagent would react with the acid in an acid-base reaction, preventing any addition product from forming. The last reactions we will discuss in this video are reactions for epoxide synthesis. There are two main methods for synthesizing epoxides: treating halohydrins with base and treating alkenes with peracids, RCO3H, such as metachloroperoxybenzoic acid, MCPBA. The following halohydrin can react with a strong base, such as sodium hydride, to form the corresponding epoxide. This reaction proceeds through the deprotonation of the alcohol by the strong base, generating an alkoxide anion and hydrogen gas as a byproduct. The alkoxide anion, being in close proximity to the alpha carbon bearing the bromide-leaving group, performs an intramolecular SN2 reaction via backside attack, displacing the bromide ion and forming the epoxide. It is important to note that for this reaction to proceed, the alcohol and halide groups in the halohydrin must be in a trans configuration on the ring. This configuration is necessary to allow the intramolecular SN2 reaction, as it requires a backside attack geometry. If the alcohol and halide are cis to each other, the reaction will not occur due to the steric and geometric constraints preventing proper alignment for the backside attack. Finally, alkenes can be treated with peracids, RCO3H, such as metachloroperoxybenzoic acid, MCPBA, to form epoxides. This reaction, known as epoxidation, involves the direct addition of an oxygen atom across the double bond of the alkene to form the three-membered epoxide ring. We will discuss this reaction in detail, including its mechanism as well as the formation of halohydrins, in a later video. As always, let's do some practice. Propose reaction sequences to accomplish the following transformation. Specify necessary reaction conditions and reagents. You may use any building block with less than or equal to 3 carbons for your syntheses. However, the reagents that you use that are not incorporated into the final product may contain more than 3 carbon atoms. The structure of the reactant and the product should be shown for each chemical transformation. Feel free to pause the video and try these problems on your own first. In the first reaction, we are tasked with proposing a series of steps to transform the starting material into methamphetamine. To determine the required steps, we can use retrosynthetic analysis, working backward from the product to identify the intermediates and reactions needed to achieve the transformation. First, we observe that the product contains 4 additional carbons compared to the starting material. Additionally, the product involves the formation of both carbon-carbon bonds and a carbon-nitrogen bond in the methylamine group. Since amines are good nucleophiles, this suggests that the methylamine group could have been introduced via an SN2 substitution with a good leaving group, such as a halide. Examining the starting material, we note that a direct transformation from the aryl bromide to the final product is not feasible in a single step due to the complexity of the carbon-carbon bond formations required. However, if the bromine atom were replaced by a secondary alcohol, this intermediate could then be converted to a secondary bromide without rearrangement using phosphorus tribromide, PBr3. The secondary alcohol could be synthesized via a Grignard reaction. Specifically, the Grignard reagent, prepared from the aryl bromide starting material, could react with propylene oxide as the electrophile. This reaction would result in ring opening at the less substituted carbon of the epoxide, yielding the secondary alcohol. Using this retrosynthetic analysis, we can now outline the forward synthesis for this transformation. In the second reaction, we are tasked with transforming the halohydrin starting material into the given product. Using retrosynthetic analysis, we can work backward from the product to identify the necessary steps. First, we observe that the product contains 3 more carbons than the starting material. Additionally, the product features the formation of both a carbon-carbon bond and a carbon-oxygen bond. Importantly, the product contains a tertiary alcohol, which is absent in the starting material. This tertiary alcohol could have been derived from a ketone through a reaction with an ethyl Grignard reagent, followed by an acid workup. Taking a step further back, the ketone could have originated from a secondary alcohol via oxidation. Oxidation of a secondary alcohol eliminates any stereochemical configuration relative to the hydroxyl-bearing carbon, so we will proceed with the given stereoisomer for this synthesis. At this point, the compound resembles a ring-opened epoxide, where methanol acted as a nucleophile, attacking the more substituted carbon during an acid-catalyzed epoxide ring opening. This step brings us back to the epoxide intermediate. Looking at the starting material, we can see that the anti-stereochemistry of the halohydrin makes it a suitable precursor for epoxide formation. Treating the halohydrin with sodium hydride NaH will deprotonate the alcohol, forming a strong nucleophile capable of performing an intramolecular SN2 reaction. This results in a backside attack on the bromide, forming the epoxide and setting the stage for subsequent steps. With this retrosynthetic analysis, we can now propose the following forward synthesis for this transformation. As always, thank you for watching, and I'll see you next time.